Hello there! This video is going to give you an overview of what a hypothesis is, the types of variables involved in hypotheses, and also the difference between hypotheses and research questions. So in this video, I will emphasize the importance of considering past research before developing hypotheses. Then I'll get into what a hypothesis actually is and how to make sure that it is testable and has a specific prediction. And then I'll give you some practice looking at hypothesis examples and figuring out what is and what is not a hypothesis that can be tested with the research at hand. And then we'll end on looking at type 1 versus type 2 errors in hypothesis testing. Although the scientific method starts with an observation or a thought or a question, it's not really research until you start to get smart on what's been done in the past in the academic literature and in past research, and then start to refine and develop hypotheses to actually test. So think about starting research as entering a conversation that's already started, right? There's already researchers who are interested in similar things and are doing work to answer those questions. So it's important to jump into that conversation and maybe listen for a little while, right, by reading past research before you chime in and try to contribute to it. It's really important not just so that you're figuring out what past research has found so that you don't try to reinvent the wheel, but also so that you can identify gaps in that research that you can fill with your own research and avoid wasting your time and the time of your participants. So getting in on this conversation is important, but it's also important to go after reputable resources. So make sure that you're looking at past research that's published in peer-reviewed academic journals. And those need to be current, right? Published semi-recently, especially for things that are maybe change and evolve quite quickly over time. Also making sure that before you use a journal article to justify your own research, take a look at the methodology and make sure that they used reliable methods and that they actually provided their sources and provided ways to replicate their results. Also make sure that the sample that they're using is relevant or generalizable to the population that you're interested in studying yourself. If you start to notice that there's no past research that looks at exactly what you're looking at, that's a good thing, but you may have to be creative to find research looking at similar things to justify hypotheses. So maybe you want to look at the effect of social media on the way that we feel about ourselves. And there isn't a lot of research out there on that. But you do find that there's research that suggests that when we compare ourselves to others, and especially when we compare ourselves to others who seem to be doing well, we feel worse about ourselves. And since we know that social media tends to be the highlight reel of everybody's best and brightest moments, and that when people look at that, maybe they're comparing themselves that way, then maybe we can infer a hypothesis that says, we know when people compare themselves to people who are better, they feel worse, and social media provides an opportunity to do that, so people who look at more social media may feel worse. It's also important to consider that you may be looking at a population that's understudied, so you can look at past research from different populations and just be kind of cautious of that as you develop your hypotheses that you're looking at a unique population and trying to replicate that past research. So there's a few guidelines for deciding what is a hypothesis and then figuring out the best way to test it. So a hypothesis is really just a prediction that's based on past knowledge or observation that has yet to be proven or disproven. Hypotheses are really a tentative, educated statement, ideally based on past published research presented in academic journal articles, that really proposes a possible explanation to some phenomenon or event. The hypothesis should be specified before the research is conducted. Researchers should base their predictions in past theory, have some justification for their methodology because it worked well in the past, or these results need to be replicated to be trusted. And researchers also need to be sure that they're adding to the current body of knowledge about their topic area. So they're identifying gaps and limitations in past research and improving upon them. It's also really unethical to require research participants to complete surveys with many unnecessary questions or be exposed to manipulations or interventions or conditions that aren't really justified by past research and theory. It's also unethical to measure everything you may be interested in and then run a bunch of statistical analyses on some sort of fishing expedition and then use those statistically significant results to create already supported hypotheses. This is really difficult to resist for academics who need to publish and know that it's easier to publish statistically significant results. But developing hypotheses after the data collection and analysis can lead to errors. And I'll get into more about type 1 and type 2 errors here soon. So of course, researchers find unexpected results in their analyses and they want to report them. But it's important to report such results as a follow-up analysis and not something that you predicted to happen all along before the data was collected. Luckily, there are a variety of ways to access journal articles for free. So if you are affiliated with an institution like Marshall University, you can use the library to access tons of journal articles, and there's lovely search features and filters so you can make sure you're getting the latest and greatest peer-reviewed research. Google Scholar is also an excellent option for obtaining academic peer-reviewed research, and this is a nice way to kind of sift through the more newsy types of sources and get more into the academic types of sources. So Google Scholar is great. And if you are affiliated with an institution, you can go to Google Scholar, the options, and you can go to My Library, and you can set up your credentials so that you can do searches through Google Scholar and then use your academic or your institutional credentials to get full text free access to journal articles. There are also free options for people who don't have an institutional affiliation or access through a university, and that includes ResearchGate, where authors and researchers actually put full text versions of their research out there for public consumption. Also, the directory of open access journals and PubMed are great options to get access to free academic research presented in journal articles. So now that I've given you a basic overview of what a hypothesis is, and the importance of consulting past research when it comes to developing your own hypotheses, now let's look at the types of variables that are involved in a hypothesis. So independent variables, or IVs, are a manipulated condition or some sort of intervention that the researcher is in control of that is designed to result in some sort of change. So when it comes to hypotheses, the independent variable is the cause in any kind of cause-effect relationship that a researcher wants to look at. Independent variables are really reserved for experimental research where conditions are manipulated. But you also have situations where you're doing quasi-experimental research or correlational research where the predictor in your relationship is not manipulated, but it's measured. So maybe you're looking at a measured variable that you think is going to be related to some other variable, like looking at maybe job satisfaction as a predictor of performance, and you're measuring job satisfaction as a predictor in that model, but not manipulating it. Also looking at pre-existing differences as a quasi-independent variable. So maybe you think there's a difference in job satisfaction between males and females, or between people that work at different types of organizations. The researcher isn't going in and being like, today you're a man and today you're a woman, or today you work for a hospitality industry and today you work for manufacturing. That can't be manipulated. It's something that's measured and examined as a quasi-independent variable, as a predictor, not necessarily a cause. The dependent variable, regardless of what type of study you're looking at, if it's experimental or not, is always measured, and it is the effect or the outcome of the independent or the quasi-independent variable. It's the thing that you're wanting to see if it changes, if it depends on your independent or dependent variable. So I love flowcharts, so I'm going to show you kind of a flowchart of how to think about this. So remember, when we're looking at the relationships between variables or differences in variables based on another variable, your independent variable in experimental research is the manipulated cause, and then the effect is your dependent variable, what you're measuring, what you think will change based on what was manipulated. Notice the one directional arrow here, because we are looking at a clear causal pathway in experimental research. Now, when we're doing correlational or quasi-experimental research, here you see the double-sided arrow, because that's suggesting that it could go either direction, right? Maybe job satisfaction leads to performance, but maybe people who perform better tend to be more satisfied, and it goes the other direction, right? So keeping in mind that we can't make cause and effect inferences when we're doing non-experimental research with quasi-independent variables. But we can still, based on past research and theory, have a pretty good idea of what's the predictor and what is the outcome. So in addition to being an educated prediction based on past research or observations. A hypothesis also needs to be testable. So a hypothesis is really a clear statement that predicts the direction of the relationship between the independent and dependent variables in your research, or the predicted or expected differences in the dependent variable between pre-existing groups or manipulated conditions that represent the independent variable. So it needs to be testable, and it also needs to be specific, making specific predictions. So to be testable, hypotheses must only include variables that can be manipulated and measured. So manipulated, right, independent variables, and measured, quasi-independent variables and dependent variables. And we need to be manipulating or measuring these variables in the researcher sample with the resources that are actually available to them. So now I want to illustrate the difference between a hypothesis and a research question. So hypotheses, again, are justified by past research. They're very specific. They predict what direction or what differences you expect. But research questions are a little bit more open-ended. And as I mentioned before, if you do an analysis after you test your hypotheses and you find some cool results, you can report those as answers to research questions and be like, hey, you know, we didn't make specific hypotheses about these based on past research, but here are some questions we wanted to answer with the follow-up data analysis, and here were the answers that we got. Future research should dig into these more. So a research question is really just an overall statement about what is expected to be related or which variables may differ based on group statuses or manipulated conditions, but it doesn't indicate the specifics. So will the variables have a positive or negative inverse correlation, or which group will have the highest or lowest levels of the dependent variable? So they lack those specific predictions. So now I'm going to show you an example study and some examples of what would be a hypothesis and not a hypothesis for this study. And I want you to think about in a minute what makes these potential hypotheses work or not work. So here's an example scenario. So let's say you're a nutritionist working in a zoo, and one of your responsibilities is to develop a menu plan for a group of monkeys. In order to get all the vitamins they need, the monkeys have to be given fruit as part of their diet. So the choices that you consider include figs, bananas, pomegranates, and avocados. So those would be like the different conditions. And you know in the wild that monkeys eat mainly bananas, but you suspect this could be because they're safe while they're feeding in banana trees, whereas eating any of the other fruit would make them vulnerable to predators. So you design an experiment to find out which type of fruit the monkeys like best. You offer the monkeys all 4 types of fruit in equal quantities and then observe what they eat most. So keep this in mind as we look at these examples of things that are and are not a hypothesis. So here is a lovely hypothesis for this research scenario. When offered all 4 types of fruit, the monkeys will preferentially eat figs. So this statement satisfies both the criteria for a true hypothesis. So first, we've got prediction. So it actually predicts the anticipated outcome of the experiment. They're going to eat more figs. And it's also testable. So once you've collected and evaluated your data, like the observations of what the monkey will eat when all 4 types of fruit are offered, you know whether or not they ate more figs than fruit. This is something you can actually test through observing the results in this study. So now let's take a look at something that would not be a hypothesis for this study. So when offered all 4 types of fruit, which type will the monkeys eat preferentially? Can you remember what that is? It's not a hypothesis. It's not a predictive statement, right? It's a research question. We're not being specific about which type of fruit they will like the most. Here are a couple more examples of non-hypotheses. So when offered all 4 types of fruit, the monkeys will preferentially eat the type of fruit they like best. Think about the issues with that. Why is that not a hypothesis? Let's look at the other one. When offered all 4 types of fruit, the monkeys will preferentially eat bananas because they can eat these safely in their natural habitat. So think about why that is also not a hypothesis for this study. So these statements sound predictive, right? They're making a specific prediction, but they are not testable. Your data will show you whether the monkeys preferred one type of fruit, but not why they preferred it, right? Not because they like it best or because it's safe. Your experiment is not prepared to test those assumptions. So now let's look at another example of a non-hypothesis for this study. So in their natural habitat, monkeys that eat bananas are less vulnerable to predators than monkeys eating in other fruit trees. This is something that is technically testable, but not with this study. Because again, we're doing lab research where we're giving them different types of fruit and seeing which one they prefer. We're not out in the wild. So how could you maybe test this hypothesis? Think about it. So maybe instead you could do empirical field research in the wild, looking at how many monkeys get killed by predators while feeding in each type of fruit tree, right? But that would be a different study. So not only do you want to make sure that your hypotheses are specific about their predictions, but also that it's testable within the confines of the research that you're doing. Now, each hypothesis technically has two hypotheses attached to it. So one is the alternative hypothesis, and that is the researcher's expectation that there's some sort of relationship or difference between the independent variable and the dependent variable, right? The independent variable causes the dependent variable, or the independent variable predicts the dependent variable, or there's differences in the dependent variable based on different levels or conditions of the independent variable. So again, the alternative hypothesis is really the researcher's prediction. The null hypothesis is what's actually tested in research, though, because it's really hard to prove something true, but it's much easier to prove that something isn't false. So the null hypothesis is kind of the false assumption, or the nothing is happening assumption. It states that there's no relationship between variables, or that the independent variable doesn't have an effect on the dependent variable. So in research, and if you've ever taken a statistics class, we talk about rejecting the null and failing to reject the null. So if you reject the null, then you have found support for your alternative hypothesis and your expectations. But you haven't proved the alternative hypothesis to be true. You've just provided support for the alternative hypothesis and suggested that the null hypothesis is inaccurate. So just keep that in mind. The hypotheses that you see stated in journal articles are going to be alternative hypotheses. But when the statistical analyses are run, they're really testing the null hypothesis and hoping to reject that null hypothesis in favor of supporting the alternative hypothesis. So now I would love for you to take a moment to pause this video and go through these different examples and identify which are a hypothesis that is making a specific testable prediction. So now I'm going to go through each of these and explain why it is or is not a hypothesis. So a child's middle school GPA depends on parental involvement. That's pretty testable, but it's not making a specific prediction, right? Are high levels or low levels of involvement related to higher GPAs or lower GPAs, right? It's not specific. It's not a directional prediction. Then B, women in the 1950s felt less compelled to work outside the home compared to women in the 2010s. Well, that is going to be a really difficult hypothesis to test, right? Because we can't hop in a time machine and go back to the 1950s. Granted, we could talk to elderly people who were in the workforce in the 50s and ask them about their experiences, but that is not really going to be a great test of that hypothesis. C, managers with strong feelings of superiority are less liked by subordinates. You could absolutely do a survey research study to look at this, and it is a specific prediction because we know that those who have stronger feelings of superiority tend to be less liked by subordinates. And on the flip side, those that don't have strong feelings of superiority would be predicted to be more liked by subordinates. So far, that's the only specific prediction-based testable hypothesis. So D, students prefer different types of class formats, online, hybrid, or in-person. And this is not specific, right? This is kind of more of a research question, like is there a difference in preference of class formats? But there's no specific prediction about which class formats students prefer the most, or even better, why they prefer those different classes. E, do males and females have different perceptions about Planned Parenthood? Here's a hint. If you see a question mark at the end, you're dealing with a research question, not a hypothesis. Again, this doesn't make a specific prediction about males or females having more positive or less positive perceptions about Planned Parenthood. So now let's end on looking at errors in hypothesis testing. So there's type 1 error and type 2 error. Both are mistakes, right? Because they were called an error. So type 1 error is more of a problem when you reject the null hypothesis. When you say, there's a significant effect, this treatment had an effect, or these variables are related. But in fact, the independent variable doesn't really have an effect on the dependent variable. This is usually a function of sampling error. So maybe, let's say that you're doing a study where you are you're requiring students to form a peer support group and meet with them twice a semester. And you find that those students tended to have better graduation rates. Well, maybe the students who are in the condition of peer support were already more likely to graduate, right? Especially if you don't rely on random selection and randomly assigning people to conditions, which we'll get into more about this semester. But you may have just, by chance, had a group of students who were doing the peer support thing that were already more likely to graduate for other reasons. That's a type 1 error. When you reject the null, you say that your treatment had an effect or your variables are significantly related when they really weren't, and it was just a function of sampling error. This is a big problem, especially in medical research. If you reject the null and you say that a treatment is better than previous treatments or a treatment has an effect, people may die if type 1 error happens. Keep in mind that these errors are not malicious. They're usually just something that kind of happens by accident and it wasn't the researcher's fault. Type 2 error is when you fail to reject the null, when you say that a treatment didn't have an effect or variables weren't related when they actually were, but your sample size wasn't sufficient to detect it. So there's something called statistical power, and before you collect data, you kind of do a little analysis to see, okay, how many people do I need to have in this study to find any effect if it exists? And so if you are really confident based on past research and theory that these things should be related or there should be differences in the dependent variable based on your independent variable, and you run the study and you don't get the results you expect, it may just be time to collect more data and get a bigger sample size. So here's a little depiction of the difference between a type 1 and a type 2 error. So it's not an error if you're sick and your doctor says you're sick, right? That is an accurate diagnosis. You would reject the null hypothesis and say, you are tired and sore because you are sick, right? That's what we think is happening. Conversely, right? If you're well and your doctor says that you're well, that's not an error either, right? Because that's an accurate diagnosis. So you would fail to reject the null hypothesis, but it would be the correct decision. You're tired and sore, but not because you're sick. However, we may have a situation where an error happens. So if you are sick and your doctor says that you're well, then the doctor missed your real sickness, right? They made a type 2 error. You were tired and sore because you were sick, but they failed to detect that with their study. On the other hand, if you're well and your doctor diagnoses you as sick, that is also an error. That's a misdiagnosis where they incorrectly rejected the null hypothesis. They said that you were tired and sore because you're sick, but in fact, that's not the case. It's not the sickness that's leading to that. You're well and you're not sick. So I hope this lecture gave you a really solid idea of what a hypothesis is, the types of variables that are in a hypothesis, and how they differ from research questions. Also, I hope that you remember to always consider past research and theory and methods before developing your own research hypotheses in your own studies. If you want to learn more about this, you can check out an awesome textbook by Graviter and Ferranzo that was published in 2019 that you see right here. And there's also many, many resources online about hypothesis and hypothesis testing.